Hello everyone, let's take a look at our next problem. Give a vector proof that for a triangle inscribed within a semicircle, the included angle is always pi over 2. Okay. So we'll start with drawing a picture. I mean, this is a well-known theorem. If I have a diameter of a circle, and if I draw any triangle such that two of the vertices are at endpoints of this diameter, and the third vertex is on the circumference of the circle, then it doesn't matter where this point is, the angle here will always be pi over 2, or 90 degrees. Let's call this angle theta. And we want to prove that theta is equal to pi over 2, and it's specifically asking for a vector proof. So if my first thought then, if it's asking for a vector proof, is that if we think of these two vectors here that I'm tracing out, or at least labeling with arrows, the dot product between them should be equal to 0. That would prove that theta is equal to pi over 2. I'm going to start labeling points here. So the center of the circle we'll label as O, and I'll just label these 3 points A, B, and C. So I can now construct vectors out of all of these points. And I know AB plus BC is equal to AC. And I want to take a dot product between AC and AB and show it's equal to 0. But at some point, I'm going to have to use the fact that BC is a diameter of the circle. It may also help at some point to consider the vector AO. Like, I wonder if because if I do this, I have the vector BO is equal to the vector OC as vectors, and that BC is equal to 2BO. I'm just going to AB plus 2BO is equal to AC. And if I take a dot product of AB and AC, so that's AB dot AC is, well, it's AB dot AB plus 2BO, which is the norm of AB squared plus 2AB dot BO. Does this help in any way? Well, I can also write AB is AO plus OB. Let's see if this gives us anything useful. So I'd have 2AO dot BO plus 2 ob.bo, but ob.bo is just -1. Well, no, it'll be -1 times the magnitude of that vector squared. AO.BO. What if I write, I feel like, I hope I'm not just walking in circles here. AB is AO plus OB. So I suppose what's gone on here is I've just written everything in terms of vectors connected to the origin. Okay, so AO plus OB magnitude squared is the same as AO plus OB dotted with itself. And maybe, if we're lucky, we'll get a whole bunch of cancellation here and everything will turn out to be 0. So let's just expand this and see what happens. This gives me AO squared plus AO dot OB plus OB dot AO plus OB magnitude squared. And then I have these terms left over. 2 AO dot OB minus magnitude BO squared. Okay, so some stuff is going to cancel here. That cancels with that. Have I made a mistake in arithmetic and everything? Because it looks like I'm going to get looks like things are not fully canceling. It would not be unusual for me to make a mistake like that. Okay. I'm going to kind of, like, all this is, these are all the same, right? AO.OB, AO.OB, that's also AO.OB. So I have 4 of those. I feel like a negative sign is missing or something else. I'm going to kind of write stuff out again. And I'll badly retrace a diagram here so I can refresh my memory on what everything is equal to. Okay, so AC is equal to AB plus BO plus OC. And AB, again, I'm going to try and write everything in terms of vectors where at least one of the endpoints is the origin. Because I feel like that'll be the easiest to juggle around and see some of the cancellations later on. Okay, so AB is AO plus OB, okay, plus BO plus OC. Okay, so these in fact cancel. OB plus BO is 0. And OC is the same as BO. Okay, so we're saying then that AC is equal to AO plus BO. And yeah, that is correct. Okay, and I want to take AC dot AB. Okay, so I have AO plus BO dot, and AB we said is AO plus OB. And I think now will we get what we want this time? So this gives us AO squared plus AO dot OB plus BO dot AO minus BO magnitude squared, and this works out. These cancel because one of the vectors has become reversed. And I mean, I haven't drawn things on the circle here, but this is why it was convenient to write everything in terms of vectors coming from the origin. The magnitude of AO is equal to the magnitude of BO, so this is equal to 0. So I'm not sure what happened in my first attempt, if there was an arithmetic mistake, or maybe things do in fact cancel out and I just didn't see it properly. But yeah, this ends up being, once you see it, as usual, it becomes straightforward. But you know, translating what we're asked to prove into a vector statement about dot products was the first step. And then I guess, you know, my intuition about writing everything in terms of vectors from the origin ended up being nice and convenient here. And I suppose the main reason for that is most of the vectors involved that come from the origin are all going to be of the same length. They're all going to be equal to the radius of the circle. So there we go. This implies that angle BAC is equal to pi over 2 because these vectors are orthogonal. Thanks for watching.